For these last few lectures of the course, I'll take over from Thierry, who's done a really good job of explaining to you the foundations of linguistic linked open data. And now we're going to start to look into some of the models we actually use for linguistic linked open data. And by our surveys of the cloud and from our work, we see that probably the most used model is the one we developed, which is this OntoLex-Lemon model. And this is a model for representing lexicons, so dictionary-like information, relative to ontologies. But before we go too deep, I'm just going to give you a little bit of revision. We've already seen the turtle syntax, which is the terse syntax for RDF, but we'll just go through it again quickly so that you're clear about how it works. So, when we talk about a simple RDF document, we end up with something like this, because obviously we have URIs to represent everything. So we have a URI for Paris, we have a URI for the property of having a population total, and we even have a URI to indicate the data type of the value of its property. And then of course we have Paris, which is of type location, and Paris is maybe of type with some opaque URL here, where it's Q486972. So, when I tell you this is a simple RDF document, I think your reaction should be something like this. This is horrible. For a machine, maybe it's okay, but for a human, obviously dealing with a document that looks like that is just impossible. So Turtle is an attempt to try to make RDF a little more friendly for those of us who aren't half machine. So we do a few things in Turtle to try to make a document a little more readable. So one of the first things we can do is we can try to abbreviate all of these repeated URLs. So we keep seeing dbpedia.org/resource and wikidata.org/entity, and then this wonderful, easy to remember RDFS URL that the W3C came up with, which is wp.org/99/02/22-RDF syntax-ns. So easy and simple to remember that even after over a decade of working with RDF, I still have to look that up every time. So what we can do is we can introduce these prefixes. And prefixes are very simple. We can just say, well, instead of having to remember, let's put it here. Instead of having to remember all of this long URL, we can just shorten it to RDF. So when we do this, we can replace all of this URL nonsense with just this. So now we're starting to get to something that's a little bit readable, right? So now it's Paris. We know which namespace is defining Paris. This is the DBpedia. So we shorten just to DBP. We have population total, which is from the DBpedia ontology, which we shorten to DBO. And we can shorten the data type to XSD, XML schema description. And we can read this fairly easily. Paris population total, 2 million. Paris type location, Paris type, and we can still keep a full URL if we want to. So we can mix this together as we choose. So prefixes are the first thing to make these documents a lot more readable. Simple idea of a prefix is that we'll have at the top of our document a line that is of the form @prefix pre:, angular brackets long, and then whenever we meet pre:, name, we expand this into angular brackets long plus name. So that's essentially just what we're doing there, and it's just a very simple technique just to avoid repeating ourselves and end up with smaller, easier to read documents. So the second thing is continuation. What we notice is that this is readable, but it's still quite repetitive because we have Paris 3 times here, and we have RDF type twice here. So there is a trick that we can use to avoid repeating ourselves, which is called continuations. So one of the simple continuations is what we do is if we want to say that we're not repeating the same subject, all we do is we remove the full stop from the end of the line, and then we can get rid of our subject here and replace it with a semicolon. And we can in fact do the same here, of course, as well. We can remove this full stop, and we can replace this with a semicolon. So this allows us to say, basically, the semicolon acts a bit like a ditto here, in that we're just repeating the subject. However, we also sometimes want to repeat the property as well. So if we want to repeat the property, we remove whatever the existing punctuation is, and replace it entirely with a comma. So in this way, we're now repeating both the subject and the property and the predicate. So we can very simply do this, and of course, for most practical purposes, we'll further condense this. We'll take these punctuations and we'll put them back onto the end of lines here. So, for example, here and here. And we end up with a very complex, very simplified, terse representation of the data we had before. So this allows us to write something that's actually quite compact now. Instead of this whole slide full of URLs I showed you 5 minutes ago, we've now got it down to Paris population total, RDF type location, and the Wikidata entity. So this allows us to make a fairly compact representation. So the next thing is, we have this concept that's fairly useful in RDF because RDF has no order in terms of the list of elements. So even though in the document this element comes before this element, under RDF semantics, if I swap those two, it would be the same document, it would be the same data. So there's no concept of order. So how do we go about getting order out of an unordered structure? Well, we can use this idea that is, for the computer scientists in this room, certainly very basic, which is of a singularly linked list. So what we do is we create a node, for example here, and we give this two properties. One is called first, which points to the data, the current first element of the list, and one is called rest, which points to the next node in the list. And then the next node then has a first, which is of course in this case the second, because it's the first element of the second node, and then the rest, which when the list terminates, points to nil. So this is a list of two elements. So this gives us a way of representing the order of elements in an unordered graph. It also allows us to make things finite. So we didn't talk too much about the open world assumption yesterday, but this is a fairly key concept in description logic, that you can't assume that because something doesn't exist, it is, or something isn't in the document, it doesn't exist. That is, there is no negation by failure for anybody who is a prologist, prologue fan. So we don't have negation by failure, we don't have non-existence. So to actually say that there are exactly two elements, we need to have a statement like this saying in the graph that there is no further elements, that is, the next element is nothing. So we have to explicitly say this. So RDF lists are great, but one of the things they introduce is they introduce the idea of blank nodes. So blank nodes are nodes that don't have a known URI. They're widely misunderstood, even by people who know semantic web very well and know these technologies very well. It doesn't indicate that it's an anonymous node, it indicates it's a node that has not yet been named, which is a bit bizarre. In practice, they're often used like they're anonymous nodes. So this is very often the case in lists, where we use an anonymous node in order to mark the individual nodes in a list. So a blank node is most typically represented in a turtle document with a special namespace called underscore. Underscore is like a wild card, right? In many languages. I think this comes from Haskell. Originally, this idea of underscores a wild card, but if you've programmed in Scala, you might also be used to this. But this basically means in some namespace we don't know, hence the underscore, a node called N1 exists, and this N1 represents the node in the RDF list. So, we can represent it with an underscore, but fortunately, we get an even nicer syntax, which is to represent it with a square brackets. So it's a bit compressed on this slide. So, there is actually, Turtle has an even nicer syntax for this, which is just this. We won't use it too much, but this essentially simplifies nearly all of this down to just this little with normal rounded parentheses for the elements.
Could you explain what the full stop does?
The which one?
Like any full stop. What is the full stop at the end of our triplet?
So the full stop indicates that it's the end of a triple.
Just that it's the end of the triplet.
Yeah. It's like a semicolon in C or C++ or Java. It's just the end of line to make it nicer for the parser. So.
And you still have to put it at the end of the last triplet.
Yeah. So in this case, because this whole square bracket phrase is actually acting like the third element of this triple. So this triple has a continuation, so it has no subject. That's a predicate, and then it has this as an object. And then after the end of the object, we have a full stop to indicate that we're ending this second triple. So, finally, I'm going to talk a little bit about URLs. So, I think most people are familiar with URLs, even though they're starting to be a little less obvious in the world. I think they're still fairly ubiquitous. But I wonder how many people actually kind of understand what's going on in the URL. So, typically, yeah, I mean, I hope some of you do. This is a computer science summer school. We should know how a URL works. So typically a URL has, well, in this case I'm simplifying it to these four parts. So first of all we have a protocol. The protocol tells the computer, how am I going to find this document? So HTTP is the most, well, HTTP and HTTPS are the most commonly used protocols on the web. That's how we find most documents. And as we saw with the linked data principles, we always want to use HTTP for our data location. But of course there are other things like FTP or file you'll often see if you're looking at files on your computer in your browser. But it basically tells the computer how to find it. Next we have the domain. The domain indicates which computer we're talking to. So this is who actually owns the site that is hosting the data. It doesn't necessarily mean who owns the data, but at least who owns the site that hosts the data. And then we have this thing, which starts with a slash and goes up to either a hash or a question mark. And this is the path. So in the original idea of sort of the web, this is actually referring to a path on that computer. So here we've identified which exact computer we're talking to, and here we're trying to find which file within that computer. Now, in typical web interfaces, of course, this isn't literally going from the computer's root path. It's normally from a particular folder. But this is the idea that this indicates a single file. And then finally, we have the hash, the fragment. So the fragment is provided for the client to know where you're referring to in the document. So in an HTML document, if you have something after the hash, it causes your browser to automatically scroll down to that point in the document. In RDF, we use it the same way, and it refers to a particular element defined in a document. So that is, a single RDF document can define many URLs, but they should all be the same up to this hash, and then the hash is used to identify a single RDF element defined in a particular document. So this is the idea of a URL. And one thing that's important to note is that we can abbreviate URLs by using this idea of relative resolution. And in fact, we can abbreviate URLs by dropping any part from the left. So, if you're not a web developer, this second one probably looks quite unusual to you, but is perfectly valid. It says it's basically the same resource, but we're dropping the protocol. So we're assuming that the computer or that the client knows which protocol to use. So this is often used in web pages because it allows the client to choose the most appropriate protocol. Less commonly in RDF. However, more commonly we have path, which can either be shortened to an absolute path, so from the root of the server, starting with a slash, or a relative path, so from the current document to another document. Or, and this is perhaps the most useful thing, we can actually shorten it just to the fragment identifier. And this is a nice way for a URL in one document to refer to another URL in the same document. So we can simplify this, and this also gets rid of a certain headache that we have with RDF, that once we have an RDF document published, we can't then move it to another server without having to change all of the internal links within this, unless we use relative identification like this. So for this reason, you're going to see that most of the identifiers I use for major elements like entries are going to be hash type identifiers like this. So I'm going to talk a little about the OntoLex-Lemon model. So this has quite a long history. We've been working on it for a long time. So some colleagues, some former bosses of mine, in fact, started this back in the mid-2000s. So Paul Beutler developed Linginfo, and then Philip Simiano developed LexOnto. And at about the same time, in Spain, another colleague of ours, Elena Montiel-Consola, developed LIR. And they all sort of realized that they were trying to solve this same problem, which is that we don't know how on the semantic web to represent information about language. So what happened then was that they came together. First of all, Beutler and Simiano came together and made LexInfo, and then Montiel-Consola joined, and they have a project called Monet. And then we developed the first model called OntoLex-Lemon. So Monet was a project, a closed consortium, and we felt that there was a lot of potential impact with this. So we developed an open group to talk about more, called the OntoLex Community Group, as part of W3C. And this was founded in 2012 as an open discussion, and it was a very open discussion that took a long time. And then by about 2014, the first sort of use cases results started coming out, but the actual specification then wasn't finished until 2016. And then the group hasn't stopped, it's continuing to release results. So this year we just released the lexicography module, which further improves the ability of this model to represent stuff. So what is this model about? Well, it's about representing linguistic information. Importantly, we use OWL and RDF, so the foundations you've already seen in the last couple of days. It's really focused on multilinguality. So the idea of this model is we're not just able to represent English information, but we can represent ideally any information. We try to keep to this. We have this principle that we have semantics by reference. That is, we're going to keep using OWL as our semantic model. We're not going to try to reinvent a new idea of semantics. We have openness, and we have the use of relevant standards. So when we're talking RDF and OWL, well, RDF is actually a fairly great way to represent data, as it's a label-directed graph. So this basically means it's a graph where the links between nodes have names as well, which is a very, very powerful representation format, sometimes perhaps almost too powerful. It allows us to give a URI to each entry, which is much better for representation, allows easier reuse of lexicon data, and of course, because we have RDFS and OWL, we can even incorporate reasoning if we need to. So the multilinguality, obviously this is supporting any language, but it's also important that we didn't want to make any language-specific assumptions. So we're not going to say, oh, there's only these parts of speech because these are the parts of speech of English. We quickly find that other languages have interesting ideas or very different ideas of part of speech to some kind of English and Latin grammar. Yes. So semantics by reference is sort of the idea behind the model that is almost perhaps the most controversial, which says that basically the meaning of a word is given by a reference. It's given by saying there is another symbol in a formal language, typically an OWL ontology, which gives the meaning of the word. That means the reference can then provide very rich semantic modeling, and if we do any disambiguation, then we're doing disambiguation relative to an ontology. This means that we don't have word senses in perhaps the traditional lexicographer's way of having word senses, and this is because a sense for us exists if a word is used to refer to a particular formal symbol, so a particular ontological entity. So this gives us a definition of word census that is a little different from what you might think of in a traditional dictionary, where it's more driven by the ontology, by the semantic model, than by the lexical model. So we're also very open. We're open in the sense of the model is open, the model is extensible. It's not supposed to be a finished product that you can use straight away. There's always needs to be some kind of customization for domain or for your particular challenge. We have no unnecessary choices of linguistic categories, with no payments or any kind of restrictions in using the model. And we're also incredibly open in terms of contribution and access. So all of our discussions are publicly available on the web. You can go read every single thread that has been written about OntoLex and how we got to all of our decisions, if you so please. Well, that might take you a few weeks to read through it all, but it is there, and of course you can join, and we'd be very happy to welcome you into the discussion about the development of the model. Finally, we wanted to reuse standards, so obviously we're reusing some of the web standards like OWL and RDF. We reuse SCOS a little bit, we reuse Dublin Core, and on some of these ISO standards, even though they're closed and not particularly easy to reuse, we do take some inspiration, particularly from the lexical markup framework, and there are some strong similarities between LMF and the OntoLex-Lemon model. So, let's get to the model itself. So, I'll start by trying to really motivate why we have this. So, in our world of sort of semantic webs and RDF, we try to define concepts in terms of URLs. So we assign a URL to each concept. So, we've seen that we have OWL, we have good logic, so we're actually pretty good at representing the meaning of words in terms of logic, or at least we're okay at doing it. The problem that we saw when OntoLex-Lemon came along was that we're not very good at representing language. So, for example, if we wanted to describe the word language in English, we can just write language, that's pretty easy. Most of our NLP tools can cope with just a lemma because English doesn't inflect a lot. We go to a different language, like say Irish. The Irish word for language is changa. And we typically see it in a concept, in a context like this, and here is the same word here, changa, which has obviously changed quite a bit. So there's a lot of morphology going on here. So automatic processing is probably not going to get that this word is actually this word. They're quite different. So we're much less good at representing language. And this is really the problem that we're trying to solve with the OntoLex-Lemon model. So, in terms of linked data in the web, we might want to define, say, a particular concept. So let's take this concept that I always seem to use, which is edema. Edema is a medical concept. It's a kind of swelling under this trapped water under the skin. And of course, being semantic web people, we've defined some URLs for this. So it's in DBpedia. We have even a German version of DBpedia based on the German dictionary. So the German concept here is Erden. And of course, there are lots of medical vocabularies which define certain kinds of URLs or certain kinds of identifiers. So MESH has an identifier for it. It's in the International Category of Diseases, and it's in UMLS, which is the Unified Medical Language Service, I think. So we can just link all of these. We have the language here, and we have the URLs. So this is easy if language was totally invariant, if we all spoke Chinese where the language word never changes, but most languages aren't like that. So we actually have synonyms, we have variant terms, we have all kinds of things going on here. So we have, say, edema has an unusual plural because it's a Greek medical term, or a medical term of Greek origin, so the plural is edemata. There might be lay terms, synonyms like dropsy. And then if we want to link, all of these language terms with all of these semantic terms, we end up with this mess of a spider's web. So this isn't good, and this, ends up with a lot of triples and not very much information. So we might like to do some kind of grouping. So we'd like to introduce a URL to represent the word itself. Now we have URLs for the concept and URLs for the words. So we have a URL for edema. It can count that it has two forms, edemata and edema. And we have a word dropsy and we can say that it's another form here, and then we need only link the lexical entries to its meaning. So we've already simplified our graph here by tying together particular forms with a single lexical entry URL, so a single node here. So this is why we need lexical entries. So this brings the first question of, well, what is a lexical entry? So this is the definition, and you'll be tested on this in a few minutes, so pay attention. So, and then a lexical entry represents a unit of analysis that consists of a set of forms that are grammatically related. So this means there must be a set of forms that have some kind of inflectional relationship between one another. There is a set of base meanings associated with these forms. It basically says that there is some kind of commonality in meaning. These forms all essentially refer to the same idea. So this is similar to the idea of them all being inflectional. Thus, a lexical entry is a word, multi-word expression or affix with a single part of speech. So we make this very strict definition that a noun and a verb have to be different lexical entries. A single morphological pattern. This is that if you have a different a morphological variation. So, for example, in many languages you might have different grammar or different gender or different plurals. In these cases, different gender and different plurals, they are distinct lexical entries because they have distinct morphology. And also, finally, a distinct etymology. So the distinct etymology means that if a word, comes from a different root, if it seems to be a different word, then it is a different lexical entry. So these are the important criteria, but they have to be related and fairly strictly related. So we don't allow certain kinds of derivations, like sticking prefixes like "re" or "on" in English onto the front of words. That they have to have similar meanings. That they have to have a single part of speech, a single morphology, and a single etymology. So, going back to our example, edema and edemata, these are both related forms. They both always refer to the same disease, whether it's singular or plural. But we might like to actually start to say why a particular form has a particular property. So as we've seen with RDF, it's not possible to put a literal, so a string, as the subject of a triple. So instead we have to introduce a node here. So we can introduce a node here called a form. So this node has its own URI. And this form URI says, for example, edema is a form, the number is plural, and the actual form we're representing is edemata. So this is a URL, and this is essentially then, there's a triple here, this is a URL property, then it has an object. We have a triple for this, so this is the subject, the property is number, and the object will be plural, and then we have another triple here from this form URL, saying that its form is this literal value here. So we also want to do the same thing with meanings. So instead our meanings refer to a particular concept, so we can say we have our DBpedia edema as our concept here, and our entry here as edema, and we can introduce a linking here. When we talk about dropsy, dropsy is actually quite an old-fashioned term, even among lay usage. So we might want to tell our computer somehow that this is an old-fashioned sense, whereas dropsy generally actually now refers to a disease of fish. So what we can do is we can introduce this property dating equals old, but we don't want to put it here onto DBpedia edema because not every word that refers to DBpedia edema is an old-fashioned word. For example, edema isn't, but we can't put it on dropsy either because it's not old-fashioned when referring to this disease. So instead we need a node that captures both that this is the word dropsy and it is being used with this meaning. And this is what we mean by a sense in our model. A sense is simply the combination of a word and a meaning to give a word a sense or a lexical sense. So we define a URL here. So this node is another URL for our sense. And we can then add a triple on this, for example, saying that the dating is old. So, after finally kind of introducing a lot of the context, and hopefully you've got an idea about some of the distinctions and some of the tricky decisions. So this is The actual OntoLex model, the formal diagram of it. So at its heart we have our lexical entry. This has forms. Forms can be either canonical or other, or lexical as a superclass. We have senses. Senses give some kind of usage information. And we have ontology entities. Lexical entries can be further divided into words, multi-word expressions, and affixes. So this is another reason why we might distinguish between AI and artificial intelligence, as one is a word and one is a multi-word expression. We also actually introduced a new idea of lexical concept. So lexical concept is essentially the lexicographer's idea of a meaning. And so it is a fuzzily, extensionally rather than intentionally defined meaning. So not meaning that's given by a formal ontology, but the meaning is given by a text description. And these can be grouped into a set of concepts. So here's our simple example in Turtle. So here we have cat. This is our relative URL coming in here. Cat is an OntoLex word. It has canonical form. It's written as cat. And we can say it denotes a particular concept. And this concept can be defined as a four-legged furry animal. So here we see we have the OntoLex namespace, which is in the W3C domain, because this is an accepted vocabulary. We have the lemma, which in OntoLex parlance is called canonical form. So canonical form just means lemma, basically, or head word, although lexicographers may argue about the difference between these meanings, and do. And finally, we have our sense given by a definition. So our sense here is that it denotes a particular definition. So we can then add some grammatical information. So OntoLex doesn't define any grammatical categories, because this would be too limiting. So instead, we need to use a third-party ontology, or at least not a third party. This is also developed by the same group, but it is separate. So the idea is you don't have to use our definitions of parts of speech. But if you want to, they're there. So we could import this. So we import it with our prefix statement, lexinfo. And then this allows us to say several things. Cat is now, according to lexinfo's definition of part of speech, what lexinfo defines as a noun. We can then also use this to define our form. So our canonical form has written as cat. We can say it's number, according to what lexinfo calls number, is what lexinfo calls singular. And we have an other form. Other form is any form other than the canonical lemma form. In this case, it's cats, and it has number and plural. So of course, in most dictionaries, you wouldn't bother to list English plurals because they're very regular, but there's languages like German or Irish, for example, where plurals aren't regular and you might want to list them in nearly all cases. So let's look a bit more into lexical senses. So here we're going to have two lexical entries here. So we have bulrush and cattail. So these are both OntoLex words. We now have a sense here, and here we're starting to use we're using our square brackets, so our sense is blank node, of course. And then we give it a reference, so this is our semantics by reference, and our reference is to, I say, a DBpedia concept, in this case a DBpedia concept for Taifa. And we can add a usage. For the example, we can say the usage is British English. And one important thing to note here is that sense, reference, so this little chain of properties here. So if we have our lexical entry, and we have our lexical sense here, and it refers to an ontology. So here we use the property sense, and here we use the property reference. So we can also introduce a chain just like this with denotes. So this is a property chain. So these two triples, so these two links in the graph, are equivalent to one link in the graph here. And then we have the American usage. And we're adding, of course, this restriction on the lexical sense. So this limits when we use this sense. And particularly we're saying this is limited to saying cattail in American English and bulrush in British English. And for those of you who don't know these words, it's this plant here. You see it on the side of riverbanks. You can pull those brown seed pods and they explode. They're quite fun. But these are called cattails in American English and bulrushes in British English, or typha as the general Latin name for the plant, which is used in the DBpedia URL. So, talk a little about syntax and semantics. So, lexical entries define words without context, but we might want to know how something like a verb works. So, a typical verb usage here, know, John knows Philip. So we might want to interpret this into triples. So we interpret this into a semantic representation. So the semantic representation might be my homepage, then we have a property from an ontology called Thorough for representing social networks, and we might have a URL to represent this person, Philip Simiana. Now, because we're interpreting this simple sentence into this single triple here, we might want to know how we do it, or how in general do we interpret a verb knows into a particular triple, or set of triples. So what we need to do is we need an argument mapping. We need to know that the subject, so the grammatical subject and the grammatical direct object correspond somehow to the subjects and objects. So the third location in triple is called an object. So somehow these correspond. So we know that this corresponds to this, and this corresponds to this. So we go about doing this using what's called an ontomap. So an ontomap is a mapping between the lexicon and the ontology. So for example, we might say here that know is an OntoLex word. It has a syntactic behavior that is knows transitive behavior. So know might also act in other ways. Does if you look into any formal verb frame catalogue. And you might say transitive is a syntactic frame. The subject, this is the grammatical subject, refers to knows subject. So this is the, or we define what the subject is, we give the URL. So now we know that the subject of know is defined with this URL, and the linguistic direct object is given with this URL, so know #know/direct object. So we've given URLs to the arguments, or the argument positions of the verb to know. So we know that we now have a name for the subject of the verb know, and a name for the direct object of the verb know. So this uses the synsem module, this is the URL, and this gives us our linguistic frame. And then we can use this in order to map that to a semantic frame. So our semantic frame is our lexical sense, which also acts as our mapping. So we know it refers to property knows. So we know it's going to map to a property in an ontology. And what we can do is we can say that the subject of this property, the subject prop, is the subject here, and the object of the property is the direct object here. So if we wanted to switch around this argument structure, so we wanted this grammatical subject to be the object of the triple, and the grammatical direct object to be the subject of the triple, we would just need to switch around these two subjects. So we could say that the subject of the property is a direct object, and the object of the property is the subject. And then in the ontology, we can define knows as a property with a domain, which is person. So we know that the subject of knows is a person, and a range, which is the object of knows, so the object of knows is also a person. So this is the domain and range, which is different from the subject and object, which was different from the linguistic subject and direct object. This is basically what we just saw in the last two slides. So we have our lexical entry here. It has a sense that maps to a property in the ontology. The ontology can define things like the domain and the range. So the classes which can be the subject and the object of the knows property. So the ontology tells us that only people know people. And then we have our syntactic frame, and our syntactic frame tells us that knows has a subject and a direct object. It's a transitive verb. And then our ontological mapping essentially creates then this link through the properties it's using to say that the subject, this subject of the verb, is the same thing that is in this domain here. So it's in this domain of people. And the object of this verb here, the direct object, is what is in the range of the property knows. So it's also in the domain of people. So we also get a kind of usage restriction here. We say that the verb knows by inference can only have subject that is a person and a direct object as a person. So ontology gives us our semantic restriction. People only know people. And our lexicon gives us our grammar structure, which we can use as a basis for it. So that knows takes a direct object, so it has to have an accusative object.